Okay. So, for those of you who are actually listening to this but not in class, please make sure that you read the syllabus that is on my website. And if you are here and you've not been paying attention, please make sure that you know what is on syllabus. That includes when we are going to cover which topic. And I put the schedule of topics here just for simplicity, just so you can see what we are going to be covering then, including the exams. And a lot of the newer material that is not in the book will kind of be sprinkled throughout the semester. But my main desire is for you to first learn the basics, and then you learn other things. So all this information is here, as well as the chapters that this material is from. But if you want to follow along with another book, I will put on my course notes that are going to be outlines of what I'm going to teach. Like what I'm going to do today is going to be here. So please do follow along. And very often we are going to basically do things that are not in the course notes. But a lot of that will be hopefully, if I do not fail to record, they will be in the video recordings. So I generally record my lectures and I put them on YouTube so you can watch them later. That is up to you. But I really would like you to actually read the book, not just the course notes or the notes that are, even the simpler version of the course notes. There are some concepts that it will help you to read the book. It's not just skim through. Okay, so what we're going to do today is talk a lot about different terminology, and a lot of this is kind of going to be a lot of definitions, but this is important so that we understand each other, and then we are going to kind of throw in some ideas and kind of try to decide when something is a database and something is not a database. So this is a database systems class, right? So basically we have to ask ourselves, what is a database? And then something is a database and then something is not a database. So basically there are two different things that we distinguish between. A database management system, a DBMS, is a piece of software that you use to store a database, right? So this is a software database management system. Whereas a database is the actual data that you generally store inside a database management system. So generally we are going to be more concerned about designing a database, not designing a database management system, but learning how that operates also helps us develop better databases. So we are going to look under the hood of some database management systems. So a database is going to be a collection of data. But strictly speaking, when we say database, we mean two things. One, we talk about the data model or the schema of data, meaning that what are the rules of how I should store my data. And then we talk about the instance, the database instance. Is a set of facts that are true about the database at this current point in time. So the database instance is the one that is what is true in the world right now, whereas the database schema is what kind of data I want to store in my database. So, for example, let's give an example of a class. So let's say database systems CompSci 4380 is a class. So basically for a class, I want to know information like What do I want to know? The CRN, the textbook, the instructor, right? These are all the different attributes that I want to use. Or that if you want to look at the section, the classroom, it's basically the students that are going to be in that classroom, the names of the students and the ID of the student. These are basically type of data that I want to store for this relation. But the actual instance of what is in that table will change over time because the students in database systems right now are not the same as students who were in database systems last semester. Okay? Or that the students that are in RPI right now are not the students that were RPI students 4 years ago. So the type of data you store is the same, but the actual data changes over time. So that is a database instance. Sometimes when we don't care about the data schema because we understand, okay, we are talking about something to do with the schema, we just say database just to mean the schema, just to mean the instance. Okay, so if you're abusing language, database is generally the instance, but often the database is a collection of the schema, the rules about the data, and the data itself. So let's go back to a database management system. So what are some database management system names? And I will not know everything you showed at me, but I brought some pictures to show you. So what is an example of a database management system? Yes. MySQL. All right. Yes. SQL Server. I understand it's Microsoft. Okay. I will not write that. Yes, what else? Oracle. The evil empire. All right. I do take Oracle. Yes, what else?
MariaDB.
MongoDB?
Maria.
MariaDB. That's true. MariaDB is actually a kind of offshoot of MySQL. Or so I heard. What else? Postgres, the best database in the world. All right. What else? Actually, it's PostgreSQL. Yes. IBM DB2, the database they always want you to install, but it's so slow. Not the database itself is slow, it's really impossible to install. Yes, all right, what else? Yes. MongoDB, right? We'll talk about that in a second. And many others that you have not heard of, but existed or still exist, but are much smaller in scale. Okay? So the question is, what makes something a database management system, and what are things that are not database management systems? Like, for example, is Excel a database management system? Is your file system a database? Is Facebook a database? Right? So what makes something a database and what does not? Right? So this is generally the thing that we talk about is what are the things that we consider crucial in the database management system. Right. So this is kind of the traditional view of what the database management system is. And we are going to talk a lot about these different components and which are kind of existent in which products. So one of the things about database management systems is that you define your data using a logical model. And you can also describe how it's actually stored. Then you can query it using a query language that is not C++ or Python. But it is, in fact, a logical higher level query language. So basically the idea is that you have a logical data model and a high-level query language. So the high-level query language happens to be SQL for a relational database management system, but that doesn't have to be the only one. So your relational, if your logical data model is relational, then your high-level language is generally SQL. If your logical data model is something like RDF, how many of you have heard of that? There must be some IT students who've heard of that. Okay. Then your query language is Sparkle or OWL, something like that, right? And if your underlying language is, let's say, query language, a graph language, then you have a graph model, then you have a graph query language, something like SQL. So generally you have a high-level query language, which is nice because you can write queries by asking the type of data you want, but not write an algorithm to implement it, which is a very, very important distinction. So, the Python programmer in me will say, I'm going to write, I'll put it all in a dictionary and then write all these different things. But the problem is that sometimes, depending on how you store the data, the best algorithm may change. And instead of me trying to figure out the best algorithm all the time, let the system figure that out on its own. So this is a very interesting concept that is going to be a cornerstone of databases, which is called query optimization. You write your queries to describe what you want, and then the database actually finds the most efficient implementation of it based on how it is stored. And all of it is done using an internal query optimizing engine, which actually has been implemented with hundreds and thousands of programmer hours, right? So even though you're smart, there are lots of other smart people who have implemented all sorts of things. You can sometimes do better than them, but often they do quite well. So the query optimization is a big part of databases. A lot of people say that a database is not really massive, it's not really a database until it's massive, right? Very large data. So it should allow you to store very large data, and it should not just crap out when you have, more than 10 megabytes and say, oh, I can't do anything anymore. It just basically should scale very, very nicely. You still have to obviously invest in the right hardware, but it should not really stop functioning when your data grows larger and larger. So databases are made to work on massive amounts of data, but it doesn't mean they're infallible because, in fact, some of the largest databases found out that they cannot really implement it using Oracle or Postgres. They are trying to catch up, but really some of the biggest databases have custom systems built for them. And example of that is Google, right? So Google has such massive data that, regularly you can use a database for massive data, but at the Google scale, they have to do something very specific for, let's say, being able to store their own indices. The indices for finding when you search for a query, all the pages that have that keyword, for example. So that's the very specific kind of database that, is made for very large data to the point that sometimes even a database cannot handle that. The other thing that the database management system generally works well for is transactions. So databases kind of they evolved from the earliest databases where basically being able to do lots of changes quickly. So airline, for example, reservations, banks, being able to store data, change data quickly, and many, many different concurrent users. So transactions were kind of the first killer app for transactions, and then that's why they became successful, and that's still a big part of database culture is transactions. So transaction means is a piece of program that changes the database, And we want transactions to be supportive of concurrency. Meaning that thousands of users can use the same database at the same time without creating race conditions, meaning that unless they are really trying to change the same data, they should all be able to access the database at the same time. And if they are trying to access the same data, there are reasonable safeguards in place so they cannot really kill each other's changes. And we will talk about the right way of defining that. So concurrency, but implementing proper concurrency and allowing high concurrency. And the other thing with transactions is that once you get transactions finished successfully, so your database says that yes, you can withdraw money, here's $50. Then it better be recorded that $50 was changed in your account, right? So this is called durability. Durability means that if you change data, then that change is recorded. Despite the fact that some really bad things can happen, there is, of course, no way to get away from the act of God, right? Like if your hardware is completely ruined, you can't really do too much. But failing that, if I give you $50, then it better record that in fact your account now has $50 left. So durability is very important. So generally, a database basically implements all of these different functions. So different software products may not have all of these components. So that's why we talked about something like MongoDB, which basically does not actually have SQL. You can learn that it is, a piece of software. I still don't see what there is to teach that is foundational in them. But we'll talk about what is it that they choose not to implement and probably why. There are some databases that decided not to implement consistency or a different version of consistency because they think that that's for all people. We don't care like that anymore. It is true that there are some databases where you don't care about consistency the same way. So have you ever had a case where you made an update to Facebook and kind of the update was lost? Has it ever happened to you? It happened to me, right? So in fact, Facebook does implement the weak version of consistency, which sometimes may cause data to be lost. But they've decided that it is often rare, and probably it's not going to, cause the stock market to crash, right? If your latest update is not recorded on Facebook. So there are different versions of consistency, and there are different subsets of these implemented, but a lot of the top database systems will implement a lot of these. So let me see if I can find you some of this data just so that you can see. So I was looking this morning at the database market. Okay. So this is what the global database market looks like in terms of the billions of dollars of different technologies. So this is kind of over the years, and this is projected to 2017. So the green is all relational databases. So with relational databases, we need things like Postgres, Oracle, SQL Server, MySQL, and MariaDB, and so on. And then the black part is NoSQL and Hadoop. So it is grown a little bit over the years that I have taught this class. It's still percentage-wise, it's not growing as a percentage, but it's growing in sheer dollars, that there's more and more people using NoSQL. In my opinion, some of the people who use NoSQL use it because they don't know how to use databases properly. Because I've heard that, but that it is growing, it's a thing. And then there is actually other types of data that is still kind of out there, but it is going to continue to grow. These are things that existed, traditionally. Things like object-oriented databases were used in, for example, in design industry, in like Boeing, planes and automobiles and so on. There are graph databases that are becoming more common that are also being used to store, for example, semantic web data. So there's RDS and so on. There's like a different niche data models that still exist, but you're still solidly relational databases are the top thing. So let's look at the ranking of what they look like today. Okay, Oracle, the Death Star, still is at the top. The reason that I don't like Oracle is that Oracle's business model is to give you a product that's hard to use, so you pay a lot of money for consultants, but it's a great job for you. Right? If you learn that, you're going to have a great business, but they are very aggressive sellers. What I read is that MySQL is going down over time, and Postgres is always around. Postgres is an open source database system. And it is actually bundled into lots of other big enterprise products. So it's like, even though it's going down, it still is very relevant. And SQL Server, depending on which person's data you look, sometimes it's up, sometimes it's down, but it's always in the top three. It's a very scalable, easy to use, good database system. And then MongoDB has been going up. Is MongoDB the one that Facebook released? That's Cassandra. Who's the MongoDB? Is MongoDB Hadoop?
No, they're just their own thing.
Just their own thing? All right. The thing that the last time when I looked at these, they were so badly documented, they were really hard to use. So if they're going up, that means they have finally figured out documentation. Same is with Cassandra. So you will see that there are different names, right? So you have relational databases, and you have things like document stores, okay, for storing actual textual data. You have wide column store, which we're going to talk about what that means as we go into a little bit more storage. And you have key value stores. So key value stores are very, the wide column store is basically a way to distinguish your hot data and cold data. We'll talk about that. Then the key value store is basically being able to get specific pieces of information given a key, like all Amazon infrastructure is built on stuff like that. So there are different models, but the relational data model is by far the most common. So this is what we're going to look at first, but then we're going to discuss the changes. And I'll show you one more. These are random pictures I found on the web, so we hope that they are actually true. So basically this has two axes. This one is ability to execute, and this one is completeness of vision. So basically, a lot of the time when you buy a database, there are lots of different components. Like I talked to you about a bunch of things like query engine and optimization, transactions, but there are lots of other things. So if you're designing a big size application, you have to work on workflow management and schedule jobs and index advisors, and the more you go up into the enterprise, that they have all these different tools. And Oracle is the master of those, right? Because they have so many products they are willing to sell you. And a lot of the others that you don't see Postgres here, but a lot of these actually have Postgres bundled in them, like Enterprise DB. So you see that, for example, MongoDB is not really as fully functional. So this is basically whether they support multiple operating systems. This is whether they support different functions. And so you have a lot of things all over the place. They support some of the database functionality, but not all. Okay. So what we are going to talk about is mostly things that are kind of around here, right? We are not going to care about some of the enterprise stuff, but we are going to really talk about things that support everything. And then you can choose when you're designing an application whether some of them are not necessary for your application. Okay? So So we talked about the database administrator is the person who designs the data model. Database programmer is the person who writes the SQL and other applications. And the database systems administrator is basically a person who installs and tunes a database. And database systems administrators, or DBAs, are they have their own niche group. There's actually a database, Postgres database administrators group in the Albany area. They meet regularly. It's like a special group, and a very well-paid group. So when you learn enough about one database product and you can do all sorts of things to tune it, then you actually are highly employable. So some of the stuff we learn will get you started in that if you want. So let's talk about a few basic things. So a database management system is basically this big piece of product. So there are lots of pieces to it that, you often imagine that your data is sitting at a cylinder somewhere. This could be a single file or multiple file systems, multiple machines. All right. Think of that like sushi, like put some roll on top. Okay. So given what we talked about, is Excel a database system? So Excel does not support transactions, right? And Excel does not support a high-level query language. It does store your data, so that's okay. So it doesn't really have any of the others. How about your file system? Your file system actually has some database properties, right? It actually indices your files. It can search it, even though it's not a high-level query language. It has some sort of consistency, but not really fully. And Google actually has many databases that runs it. So, it has many, many different parts. But, so your data sits somewhere on disk. And then you, as the person, write queries. In fact, your queries can be things that define what type of data you're supposed to store. So that is generally called data definition language. Or DDL. Or it could be queries that basically are generally called data manipulation language. And the thing is that they are all part of the same standard. So in the relational database management systems, DML and DBL are basically all based off the same single language. They are simple, they are different statements, but the same standard applies. And in fact, they have some of the structures shared between them. So these are generally both SQL in relational database systems. So when you get a system parsed, right, then the next thing is that you actually have to execute that query. So the thing that you need to do is, given your query, you have to figure out how you're going to execute by optimizing the query. So once you do query optimization, you're going to come up with a query plan. The query plan has to do with how you actually store the data. So not only which relations exist, but also which data is stored in, which indices exist. So there is actually a storage manager that stores that information. So storage manager has things like indexes and file spaces, and if you if you've distributed data in multiple places, whether it's replicated or not, there's lots of different components. Okay? So once you have run through query optimization, you get a query plan. Then you basically have the query execution engine. So what does the query engine do? Query engine will basically keep track of what you're doing and maintain buffers, right? So basically keep certain pages in memory, shuffle some out, shuffle some back in. So it's going to work with a buffer manager. To get the data that it needs to find the results and return it back to the user. In addition to while it's executing its queries, if it's changing data, it has to worry about whether other people are looking at the same data at the same time. So you have to keep track, you have to keep track of what the users are doing, what they're accessing. So you have to have some sort of concurrency control. And you also have to keep track of who's finishing their jobs and who's still running their jobs. Because if somebody finishes their jobs, I want to make sure that I record that, and I will write that down to disk, so that that change is never lost. So you are going to have a log manager, something that you will keep track of the log, which also is written to disk periodically. Could be the same disk, it could be a different disk. But you need to make sure that if somebody is told that you have finished your job, that I've actually written it somewhere. And so this is kind of the biggest thing that you get a database management system, all different pieces, and there are many different ways that they can be customized. So that's why you're taking this class, so that you can understand all components. Any questions? All right. So that was kind of simple. If you're done. Now, whenever you're talking about transactions, another thing that you're going to hear, all database management systems support assets. Okay? So this is a desired property of database management systems. And these 4 properties are things that all database management systems are trying to implement properly. And it is actually very difficult to do correctly, so that's why you buy a software that actually does this. Okay? And we are going to do many classes on transactions, but let me try to kind of explain to you what that means. So since you have a piece of data that many people are reading and writing at the same time, you need to make sure that they cannot read incorrect data. Okay? So, have you ever been in a plane where they sold the same seat to people? Right? So that's technically a bad thing that occurs, but it's actually, that occurs because of design, not because of database failure. Because in fact, they do sell multiple seats, assuming that some will not come. But that is the kind of idea that you can have bad things happen if your database does not implement asset properly. Okay? So one of the first things is that a transaction is not a single change. Generally, you have to change multiple things at once. So if you are withdrawing money, that means or you are transferring money, you are withdrawing from one account, subtract here, add to this one, right? So you have 2 pieces of operations that together make up a logical unit called, what do you call it? Transfer, right? So the transfer is not just the subtraction or the addition, but the 2 of them from one account, then you better deposit into the other account. Or if you deposit it to this account, you better subtract from the other account. You cannot just do it halfway. So if you just add to this account without subtracting, what you have done is you make money. Okay? It is possible for Bitcoins, but not in real life. Right? So you cannot just make money. So you have to make sure that when you wrote a transaction to do both of them, they either both complete or none of them complete. So A means atomicity, all or none. Meaning that either do all the changes or do no changes whatsoever. The second one is called consistency, which basically, when Stacy taught her class, she sent everybody to ask me what consistency meant. And I understand it's one of the more fuzzy concepts. But the idea is that your schema has some rules, right? It says what is a valid data, what is not a valid data. And you want to make sure that a transaction, if it succeeds, cannot violate those rules. So remember that no system can ever overcome stupidity of the program. Right? So assuming that you wrote the rules correctly and you wrote the program to follow the rules correctly, the system should not violate these constraints. And we're going to talk a lot about that. So make sure that the database will always make sure the data is consistent. I is for isolation. That's the easiest one for all of us to understand. The idea is that when you're writing your program, you don't write as thinking that while I'm changing this data, make sure that this person doesn't change it, this person doesn't change it. You actually don't need to care about who is accessing your data. You write your program assuming you are the only person accessing that data at that point in time. It's up to the database to make sure that that happens. In fact, even if it doesn't happen, its changes will be as if there was only a single person accessing the data at a point in time. We are going to talk about isolation rules and how to satisfy them. So that means that the changes that you make will be as if only a single transaction was executing at a time. So all right. And the last one is durability. This is the one I talked a lot about. It basically means that if you succeeded in completing your change, if your transaction completed, then I will tell you that you have for sure recorded that change to disk. That the change is never lost. So think of this as if a transaction succeeds, then its changes are not lost. So the famous example that I will give you with that is when, unfortunately, 9/11 happened. There was no loss of data. I mean, almost no loss of data. Because of, obviously you have to implement things so that you have multiple copies, but the point is that the data itself was actually recorded. The data was not lost. Or any other stock market event when things went strangely, they were able to go back to see what has happened. So the point is that, even in these super fast transactions, there is a way so that the data is never lost. Now that's an extreme example. There's different ways that has been assured, but that's the point of having a database, to make sure that you do not lose data. Okay? Even in extreme, very high throughput operations. So basically the idea is that there are some basic definitions for these, and we are going to see them in this class. So when I say isolation, there is a definition of isolation. But some of the more recent applications will say, well, I don't like this kind of isolation. I'm going to have a different kind of isolation. So they will implement a different version of it. So that's what you get in slightly different products. So I know there's a lot of definitions, but these are things that we have to talk about. So we are talking about the same language. So let's now talk about data model. Okay. So what I want to talk next, and then today will be the last, is the relational data model. And then we will talk about actually how you query it, and then what makes a model good or bad, and so on. So basically a data model or schema tells me what type of data that I'm going to store in my database. Okay? And there are different ways you can model your data, and relational data model happens to be one of them. So it was not the first database that was implemented. The first databases that were implemented were hierarchical, in the sense that you have A has subcategory B, B has subcategory C. It's actually some of the, I'm going to say maybe MongoDB, or some of the NoSQL databases want to go back to that one for some reasons. But the problem was that those databases were difficult to implement because there was no logical basis for them, no mathematics. And ultimately, relational databases became popular because the model that they have is very simple. And the simplicity is very important. So the relational data model is surprisingly simple to think about. And one of the first people to write that code got the Turing Award, after many years. But it's like one of the very foundational and simple ways of looking at things. It borrows from math and borrows from logic. So the idea is that you store your data as relations. So basically, a database is a collection, a set of relations. Okay. Now, whenever I write these things, they're going to have a very particular meaning. Okay. So in the first part of the class, you have to pay a lot of attention to this. Whenever I say set, that's important. So a database is a set of relations. Each relation contains a set of tuples. So each relation contains information about some real-life object or some concept that is relevant to your application, and so it contains a set of tuples. So the relation schema has a set of attributes and each attribute has a domain. So the domain means the set of valid values. So for each attribute, we define what are the values that are valid. Okay? And that basically is one of the constraints of what is allowed in this database. And here's a very important rule that each domain is simple values. things like integer, string, Boolean, datetime, or a description of those. What is not allowed is you are not allowed to have a structure, you are not allowed to have a dictionary, you are not allowed to have what else? A record. Each value is a single simple value. So, and that stupid thing is very important. So important that it even has a name. This whole thing is called, oh, there we go, first normal form. We don't talk about it as a thing anymore, but it is, in fact, the first normal form. That every value that you store in a table, in a relation, is a simple atomic value. So you can have an integer, you can have a string, but you cannot have a record that has two separate values. For example, you can have an attribute called name, but you cannot have an attribute called name that has two subparts, a first name and a last name. All you can have is then two attributes, one called first name, one called last name. You cannot say the combination of two is the name. It is guaranteed to be a very, very simple data type. And that's going to be very important because we are going to talk about how modularity of this data model allows you to do lots of interesting things in a simple way. Okay? So whenever you describe a database, you inevitably put things in a table because relations are actually stored in tables. They are stored in databases in the form of tables. So if you think about that, you can write that as a table which will have attributes So I have this simple table of the Avengers. So if my table is storing information about the Avengers, okay, so I can have things like the attribute is the name of the hero and the gender of the hero, the year they were introduced, the URL that they point to. So what are the data types for name? String, gender is string. Now, you can have a data type that is a restriction of a string, right? So you can say it's a string that can only be female or male, right? So you can have a domain that is simple but still has, fixed set of values. But you cannot say that it has a substructure, right? So URL is a string. You can have, you can say it's a string, but it should satisfy this regular expression, that is fine, and year is possibly integer, right? So now, here's an important thing to remember, that every name that you learn has both a logical name and a physical name, okay? So a relation is the logical concept. When you store it in a table. So a table and relation are the same thing. In a way. But remember, when you store something in a table, it's a physical implementation of a relation. Okay? In the same way, each attribute in a table is also called a column. Okay? Column and attribute are the same thing. And then we can store information regarding different, let's say, heroes in here. So I can have Thor and Jessica Jones. Is that right? All right. I still have not seen it all because it was too disturbing. Um, she's an Avenger. That's, that's right. All right. Well, this database actually is on our course website. Uh, I use nothing but real data. So you can see Thor was introduced in 1963, and Jessica Jones was introduced in 2010. Um, bless you. So, all right, let's put Peter Parker is apparently an Avenger. That seems wrong to me. All right, but we're gonna put Tony Stark here, just so that we have one more. And Tony Stark was. All right. All right, so each different tuple is basically an instance of an Avenger, right? So, like Tony Stark is a tuple, but it's also a row. So let's put the physical first. You store it in a row, but in fact, it's a tuple, right? So one is the mathematical name, the other one is the physical name. So when we're talking about the relational data model, we actually don't care about how it is stored. We are talking about the meaning of what it is to have this kind of relation. Okay? So, so this relation called Avengers has how many attributes? 4, right? And how many tuples? 3. Okay? So currently, as far as my world is concerned, there are only 3 elements, right? Because the point is that my database stores everything that is true about the world. As far as this table is concerned, there's only 3 of them. Okay? Which is a weird collection, but so be it. Okay? So the instance of this relation is these 3 tuples. So generally, the instance is about what is true about the world right now. So what's true about the table Avengers right now is these 3 tuples. What is true about this class is all the students in this class right now, right? So you are the database class instance right now, but next year is going to be a totally different set of students. So the relation, I said, is a set of attributes. Okay, so this is important. Whenever I say a set, okay, 2 things are true. It means that it doesn't really make sense to have 2 copies of the same thing, right? There's no meaning to have 2 attributes called name, right? Why should I tell the same name 2 times, right? If I have a different attribute, it should have a different name. So attributes basically have to have a unique name, and there's a meaning attached to it, and the ordering doesn't matter. If I were to store, let's say, these 4 attributes, but store the URL first, and then name, and gender, and year, it will still be the same relation, right? It will still describe the same hero. It will still be the same information, it's just that ordered in different ways, right? So when I store it on this, obviously I have to put it in a certain order. That's why I say this the physical order, but it doesn't really matter. Logically, it's the same. The ordering of these tuples, is it important? Right? So does it matter that Thor is stored before Jessica Jones? All that I know is they are all instances of this relation, so the order in which I store the tuples is not important. In fact, what if I stored the same tuple 2 times? So I stored Thor, because he's so mighty, 2 times. Did I put some new information in this table? No, because it's still, I told you Thor was an Avenger and that this is the information. So I actually did not create something new. So the point is that logically, I should really not repeat information. So that's why it's basically the same information if I repeat it or not. So really the meaning of what who is an Avenger is basically the unique tuples in this table, the unique tuples in this relation. So that's why I say that it's a set of tuples, meaning that it doesn't say anything new to logically repeat the same thing over and over for emphasis. So it's basically putting a tuple is a logical statement that Thor is a Avenger, and repeating it doesn't matter. And the attributes are basically just properties. So the way I put them in specific order is not important. I could represent the same information by extracting it, writing it in a JSON object. I don't know what JSON is. If not, don't worry. Or a data dictionary or some other format. It's just that I am saying that the name of this specific hero is Thor and the year is 1963. So that's why we're talking about the logical data model. Okay? And the most important thing we have learned so far that it has to have a simple value. All right, so now the last one we're going to talk about is each relation has a key. At least one, but can be more. So now this is going to be a little bit more tricky. Okay? Each relation has a key. It has it by definition because it's a set of tuples. Okay? Let me define you what a key is first. So a key is a set of attributes such that no two different tuples can have the same value for the key. Okay. Remember that the relation can have more than one tuple, more than one key, but each relation has to have a key. And you can think of a key as a way to identify a tuple. So key is a way to So as we get more sophisticated, we are going to say that unless you tell me what the key is, I have no idea what you're storing in this relation. Because without that, it has no meaning. So let's try to talk about some examples of relations. So let's say student. If student is a relation, what is the key for a student? So no two students should share the same value for ID number. So at RPI it's called ren. Okay. So that means show me the ren, I'll show you the student. Right? Okay. So if I look at in my database, if I find this two students with the same, two tuples with the same ren, then I default expect that they also have the same name and other attributes, right? Because otherwise it would not be a good situation for that student, right? So the ring number is unique. Do we all agree with that? Is there another key for students? Oh yeah, that's the RCS ID. I agree. All right. Years of teaching CS1, I never asked for RCS ID people to write it there. So, my brain is burned. Is there another key for students? ISO. Oh yeah? You mean like to identify you here on there. Is there anything else? Yes? Oh my God, how many ideas do you all have? All right, so how about SSI? So whenever I give this example, there are always objections to stuff I say, so I like that. So how about SSI? Do we agree that's unique? Yes? You might not have one and you might get a change. You might get a change is okay, but you might not have one I have a problem with, right? So generally, if something is a key, it must always have a value, right? Which can change, but it must always have a value. Whenever I bring this, sometimes people say I'm a transfer student or I'm a, visiting student. Do you have any visiting students? Yes. Do you have any of that? Social security? You don't. So you cannot have a key that doesn't have a value, right? Always have a value. But you can have more than one, right? How about for course? Okay, so given a course, what is the key? The CRN, okay? And now I'm going to ask different ones so that we can have the conversation here. Yes?
The topic and level.
Outside, like CSI 4380?
Yeah.
Topic plus course ID, like outside 4380. Any other ideas? No? Okay. So do these keys define the same thing? So can two courses with the same course ID and number have different theorems because of section, right? So these two are different courses, right? They are different classes. So depending on what the key is, you actually are defining a different thing. So this defines a section, right? A section in a specific semester, whereas this defines a specific class, like this class. So there's a class, CompSci 4380, but there are different sections of the common semester in different semesters, right? So that's the distinction that's important. So is there another way to define a section? Let's see. So we said that CRN is a key. Is there another way to define a section uniquely? Yes.
Time stuff. Like for meeting time.
Meeting. Meeting time and place?
Yeah. Though if you put the meeting place and then not the time stuff.
Okay. But meeting time and place, what if you have close listing? Do they count as the same class or different class? Right? So like this class is not close listed. I'm not saying that's wrong. I'm just saying to finish.
Oh yes, of course. I mean, if you put the meeting time location and location in, then theoretically, unless there's two classes taking place at the same time, same place, then you will not be close.
So it's technically the same class, but you will not be able to distinguish between the multiple sections and so on. So this is the question, right? So you basically have to think. There is not a single right or wrong answer, right? So the way you define it will define what it is. More answers? Yes. Yes.
Section ID.
Well, you still also have to say semester and year. Yeah. Right? So all right, so you can actually define the same. That's why they came up with CRN, you think. Semester, year, section ID, plus course ID and class topic, right? Something like this. So this is guaranteed to be unique between two sections, two tuples, right? Uniquely identifies it. Okay. All right. There's one last one. How about a book? What uniquely identifies a book? ISBN number. So so let's say we have a book. The key is ISBN. Okay? Well, so is anybody else by the way? So if you have bought the book, will your book have the same ISBN as mine? So ISBN will it distinguish between my copy of the book and your copy? No, right? So the point is that when you define the key, you define what you're storing, right? So that doesn't mean it's wrong, it's just that that's the book. So that defines the book as this material, but not this specific copy, right? So that's why it's important to know what your key is, because that tells you what you're trying to store. Okay? So now coming back to the last one, that each relation has a key. Even if I did not define exactly what the key is for a relation, by default, all relations have a key. Why? Because you can never store the same tuple 2 times, right? And two instances of the same tuple are going to be considered the same thing. So that means by default, if you didn't have a key, all the attributes in the relation is a key, because you can never have two tuples that are different but have the same values for all the attributes, right? That is the largest key you can have, but you may have a subset of those attributes that are key, and you can have many different subsets that are key. Okay? But the important thing is that the key defines the meaning and the uniqueness in the relation, and that's a very important part of what that relation means. This is a logical data model. So if you were to implement this in Oracle or Postgres, this is not going to be exactly true. So the logical data model is based on a set of relations, and we are going to use that to define our database. But when we implement, we are going to get rid of some of these assumptions, because database implementers decided that it would be too costly to implement set semantics, so they decided that customers don't love set semantics, so they implemented a bad semantic. So what that means is that what is really implemented doesn't require you to have a key, and doesn't really require you to not have duplicate values in a relation. That's why we're going to talk about that later on, but for now, we're going to stick with the sets. Okay? So I'm going to stop right here, and I'm going to redo these on Thursday, and then actually start working on relational algebra